So, waiting for the folks to connect. We have 2 concurrent viewers. One concurrent viewer. Mazza, se ne sono aiuti. Everyone went. But why? Because they don't. Oh, I'll discover. All right. Now, second part of the lesson with an empty lecture hall. We will see the matrix class. So we have seen that the vector class, similar to what we have done for the vector, we could do the same for the matrix, which means embedding the scalar type, which I recall in one lesson we will be changing the scalar to different types, complex or whatever they are, and having static size matrix, which means that we know at compile time the dimensions. This in turn means that a matrix will become a matrix type with its own dimension. That means a matrix 2 by 2 of float will be different by the type, will be different of a type of a matrix 3 by 3 of float. Okay? Same as what we have done for the vector. Remember that once you do the template thing, you are effectively instantiating a new type. Okay? That clear? All right. So I hope I'm taking questions about the vector class, if any, if you had a look or you were as is healthy eating. Was it? I mean, my feeling is like, was it clear enough for you, the code that we have seen for the vector? Yes, reasonable, let's say. Of course, that's the gap, because you see a new language and all sounds foggy. The important thing is that one reads bit by bit and understands more or less what you have in it. Now we'll see a little bit more complicated example that will unleash also the reason why in the templates, once you are referring to the object of the same type inside, you have to write all that huge things that we have seen in the tree case, for instance. When we wanted to refer to the type tree of int, we had to write all the templates arguments in it. Okay? And we see the matrix class. Now, I'd like you, that you are in the classroom, now I will take advantage of that. Taking advantage of, once again, ignore this namespace thing. What are the arguments that or let's do this way. What are the template arguments that I might need in defining a matrix class on the matrix class? Yeah. Not cooperative, also this thing. What are the arguments, the template arguments? What are the types that I need to, the values, the template parameters for a matrix class? In the vector I had the type of the scalar, which was a type, and I have an integer, which was a dimension. What would I need in the matrix class? Another integer. So I will have rows and columns, right? So scalar, rows and columns. Very good. I might decide to represent, to store the matrix as a linear vector, as a linear array, as we have done in the previous thing. I might also decide to use the specific bracket. So it could, at this point, given that the dimensions of the matrix are known at compile time, I could instantiate a multi-dimensional array directly. But for symmetry with the other case, I'm not going to do it. I just use a plain array, which will have dimension, so rows times columns values. Okay? As storage. All right, so let's see if this was true. I have a matrix. These are the template parameters, and this template clause at the beginning rules the entire scope that it's on the bottom. Okay. Then mat underscore, and then once again we fetch the scalars, and once again we fetch the parameters so that we can remember them. Okay, rows, columns, and then given that it's a constant and it's evaluated at compile time, I just save a multiplication and I store something that I will call dimension, which is the number of elements of the matrix. Okay. Again, we need to define this type, as we did for the vector, to simplify our existence when we do copy and other things, when we do plus equals. I mean, if we want to, with this template language, if we want to implement the transposition of a matrix, okay? The transposition of a matrix. So when you invert the rows and the columns, the transposed matrix of a matrix which is non-square will be a different type, because the dimension of the rows and the columns flip, right? So we could invent a new type and call this type transposed, which is a matrix or over the field of scalar, which has the number of columns as the number of rows, and the number of rows as the number of columns. Huh? Is it? I think it's legit. I mean, of course, we could also not do all these usings, simply that the code will become larger and larger, as we have seen the example before. Also, it might make sense, if I want to implement a vector matrix multiplication, it might also be useful to have a column vector type, which I define to be a vector, defined over the scalars, having rows elements. And it could be also useful to have a row vector type, which is a vector defined over the scalars, having a number of elements that is equal to the columns, because it's a row vector. Okay? So why do you need that? I don't, I repeat, it's only sugar for me later on when I'm gonna work with it. But, and this I hope clarifies a bit, or tells you why the added complexity of explicitly instantiating a template inside when you want to define a type is required. Because, for instance, if you want to compute the transpose of the matrix, you need to be able to instantiate a template which has different rows and columns with respect to the self object. Okay? Well, then let's go through the implementation. Plus equal is the same as the array, because I have the plus equal matches if I have on the other side of the template a type which is equal to myself. In this case, the template matches. Okay? And it returns a reference to myself. Same as the plus equal of the vector. Okay? Minus equals. Pleasant. Times equals. Like if you smell some copy and paste, you smell it right. Times equals is exactly the same. Do you have doubts on that? Is that clear what we're seeing? Very good. Then we have something which is a little bit more funky. I want to implement the multiplication of a vector by a matrix. Okay? So, if I want to implement this multiplication, I need to have a condition. I need to have that the vector must have a number of elements equals to the number, to the columns of the matrix, in order to successfully implement this product. And the return value of this multiplication will be a vector which is as tall as the matrix. All right? Understood? All right, well, that's exactly what we have written here. We have an input vector, which is row vector type, which is what applies to the right hand of the operator star. So this matches with if I do A times B, A times V, where V is a vector having dimension equals to the columns of the matrix. and the output will be a column vector type, which is a vector. Why? What is it? I mean, I could explode the business here, right? If you like it, it's like only that it becomes humongously ugly. Oh. Now, if you read it better this way, I don't. Scar calls. I mean, here there's, I could also, given that I used I redefined the thing, I could also remove the underscore. Okay? Do you see it? Oh, interestingly, applying an operator star generates a new type without explicit instantiation. Okay? Do you feel it somehow? It's legit. All right. Shall I go back to the column vector type and the row vector type, which is more elegant, or do you want me to leave it this way? The same? Right. Of course, transpose. The transpose will return a this type transpose that I could expand by expanding the using that I have defined before and calculates the transpose. Remarkably, I could also do transpose in place because transposing, but I don't do it. But you could do it because transpose in place transposes the self object. Given that the storage, the size of the storage doesn't change, you don't need to copy to transpose yourself. You only need to have a variable that keeps like the exchanges. Okay? But I just did the return a new type. Do you have questions on the transpose? Well, do you have questions on the operator start by a vector or not? It's a multiplication of row of matrix vector just implemented. No? For each row of the matrix, what do? You take the vector, you take the corresponding row, and then you do a dot product, basically between the corresponding row and the vector. And then that's going to be the result of the corresponding element of the resulting row of the product. I mean, this is... I think it's obvious, but matrix vector multiplication. If you have you ever done in your life a matrix vector multiplication with a program? That's it. You take a linear algebra book, you copy the formula, and that's what you get. Right? Oh, of course, the at method is the at method that takes now a row and a column, okay? Because at locates an element in the matrix. Where is the at method? Where did here. I have here the at method in two flavors, which is consistent with the at method of the matrix that we have implemented on the heap in the exercise that you didn't, that was implemented as a solution. And also, given that I like, maybe in my existence, I would like also to access the matrix linearly, I overloaded the operator, the function at, so that it matches also if I call at with a single number. If I call at with a single number, I'm going to access the matrix as if it was a linear array. Okay? Anyway, this was the operator, what was it? Multiplication by a vector. Transpose, of course, you create a new type, which is called this type transposed, and then you copy the elements, flipping the row and the column. Okay? Guys, if you want me to stop, I will stop if there is something unclear. I'm going fast because I assume that this is super elementary linear algebra and that you know the linear algebra part, and then you match visually these sort of things. But if you want me to stop a second, I will explain anything you need. No? Fluid? Understandable? All right. Understandable? Okay. Operator plus. Remember that the operator plus is const. No? Doesn't change me, doesn't change the other argument of the plus, but creates a new object because it should contain the sum between me and the colleague. Minus, okay, then times minus, I'd rather not comment, star, so by a scalar, which matches a times 5, for instance. And then what do? You just like, oh, this is interesting. We could reuse the functions that we have written before. We create a new matrix, which is the copy of myself. Then you use the operator star equal that you have defined before. And then you return the new object. Huh? Write less. The same is what we have done with the minus, and the same is what we have done with the plus. If we have already done work, we don't redo work. Every time you replicate code, you replicate bugs. Okay? This way you do two things. Each time you test the operator plus, you automatically test the operator plus equals. And anyway, there's no redundant operation because the compiler is smart enough that it unrolls the code and solves the business. Okay? Then the last function that we're going to see before these stupid accessor functions are the product matrix by a vector that I asked you also to implement in the dynamic matrix exercise, but I think you didn't do it, but I hope you had an idea on how to do it. This is more interesting, because if I have a generic multiplication between two matrices, the question is like, when can I do the multiplication? The matrix on the left should be as wide as the matrix on the right is tall, which turn around means that the matrix on the left should have a number of rows which is equal to the number of columns, a number of columns which is equal to the number of rows of the matrix on the right. Okay? So I have one free parameter here, which is the size. If I have A times B, is the number of columns of B. Because this is a variable, right? I don't know it. Don't know it in this code. It's not like the transpose that I had exactly how many numbers I have on the left and on the right. So we could write an open template. Observe that here I add another template parameter inside the template. What is this parameter? It's the number of columns of the other matrix that I'm going to multiply. Okay? It's like you say, this is an integer. It says other columns. What is other columns? It's the columns of the other matrix. Okay? And then if I multiply myself, which I am scalar rows calls, with another matrix, which is scalar, because both the other matrix and me, we have to be scalar, otherwise it's not defined, the field. The other matrix has a number of columns of rows, which is equal to my number of columns, so that the product can be working. And the other matrix has a number of, the other matrix has a number of rows, which is equal to my number of columns, and the other matrix has a variable number of columns, other calls, any number. When the result, if you look at your linear algebra books, will be a matrix which is as tall as I am, number of rows, and which will have a number of columns which is equal to other columns. Right? You define a matching rule. With this template, you can put a template argument inside addition, in addition, right? Understood? Well, and then here you declare a matrix that has the size of the target, of the value to be returned, and then you do the matrix vector multiplication. Basically, you take every column of the matrix on the right, and you do a matrix vector multiplication, no? And you compose the matrix on the left incrementally. That's how to implement a matrix vector multiplication. Okay? But it works with every type. Okay, this was, you know, a little bit kicking up. I mean, you knew about templates today, so it's normal to be completely, you know, like dizzy about it. The only thing is that one uses them, and then you normally start Googling and stuff. The exercises on this lesson are rather easy. All right, and this concludes our funky matrix program, right? Like, okay, you have dimension, you have methods for accessing the beauty of the things. You have rows, calls, at, like to access the elements. These methods, as well, I declare them static. Why can I declare them? What does it mean, a static method? A static method is exactly as static as in Java. It's a method that is attached to the type, is not attached to the instance. Given that every matrix has its own, every type of matrix is a different type depending on the scalar, the columns, and the rows, the dimension will be attached. It's very reasonable that it's attached to this, to the type and not to the instance, because every size is a different type. Okay? And the same holds for rows and columns. That's why I declare them static. Understood? Clear? That's it. Let's test it. Oh. Static math test CPP. Okay, again, dear George, like in order to make you more annoyed, I added 2 template methods, just to add a little bit of sugar on the template function. We want to write a template method that takes as argument takes a type t, scalar, let's call it scalar, and fill scalar x no, sorry. Fine. That takes an object, let's call it a type t. It takes as input, the first parameter is a reference to an object of type t, and the second argument, not of the template, but of the function, is the type scalar, declared inside the type t. What does it mean? Let this type t be a matrix of scalar, float, float, int, float 3, 4. Let's say this one. Let's say this, and then now if I open b, no, 3, no, 3, oh. Math static. Is this scalar. With using, you can embed a type inside, so you can name a type that is stored inside the template class. So what I'm saying here is declare a method, call this method fill. This method will take as a first function. This function will take as a first argument a reference to the type t, and a second argument, it will take a value of type, was type is the nested type scalar is this scalar, which is inside the generic type t that I'm passing to you. Okay? Why do you need to put type name? Because the compiler is not smart enough, and then you have to tell him, hey man, this is a type name. I mean, I could remove it, and let's see if it compiles again, but I don't. Yeah, it complains. You have to help it a little bit. But the important thing is that this type, so here you're signing a contract with the user, and you're telling the user, dear user, this type t that you have here needs to have inside itself using that defines a type scalar. Is that clear? The same way that you access the member of a class with a dot on the instance, you can access the types declared inside the class with a column. More clear? You say, oh, this boy here is a type. So now it's obvious what this field does, right? It assumes that x has a dimension. So for int I smaller than dimension plus I, put the value v in the element I. That's why I implemented the operator at, both for that takes one single value, both for the matrix and the vector. Because in this way I could use this method, this generic template fill, both on the matrix and the vector. Just to be more specific, vec static vec. I know this is the most painful lesson probably of the course. No, probably the next one will be. Look at this. This is the function at of the matrix, right? I also have defined of the vector at. If I open the matrix, I will find similarly static mat h. I will find equally a method at, which is defined on a single scalar. Well, semantic is give me the element in position pos of the storage array. Okay? Both the matrix and the vector define a method that I call dimension here, that returns the dimension. Right? Correct? So this method here could be instantiated. If I pass it a matrix, a vector, or whatever, it works. And what is it doing is just repeating the value v over all elements that are contained in the data structure that I'm giving it as target. Understood? And similarly, I could implement a method that I call it fill at random, that I need it for generating data, that as difference to before, it doesn't contain a thing. Of course, this method here will not work in case in case this operation here fails, right? This is a random number generator C, returns you a random number. Here, basically, I'm filling every value of the matrix of the data structure by random number.
By rows or by columns?
Oh, doesn't matter. You mean the random generation?
Or the fill method?
The fill doesn't, the result, I mean, if you're filling with the same value, it doesn't matter where you start filling. You fill it all. Even if you fill it by rows or by columns, it doesn't change much, right? And if you fill it at random, you're filling it at random. So the order doesn't really matter. I mean, technically, this is row major because you go this way in the array. Okay? Your colleague asks, do you fill by rows or by columns? It doesn't matter because it's the same. Okay. The test is quite simple. You declare the vector, you declare a matrix that you call mat3f, where here we have all the usings. This one. Here are the usings. Just to vec3f is a vector of 3 elements. Mat3f is a matrix 3 by 3. Mat3,4f is a matrix of float 3, 4, for instance, right? We have these two things, and then we can declare a vector. We populate the vector. We can declare a matrix. This is a matrix 3 by 3. We can print it. We can declare another matrix. We can fill the diagonal. We can print it. We can stimulate our operators and see what happens. Oh, it's interesting because we can write expressions, right? As before. Okay? Understood? But the thing is that the complexity, if you want to use templates, is quite easy. You just instantiate them and then you have the type ready. If you want to write it, it's a little bit more complicated, but it's mostly syntax, right? Like the important thing is that you try to figure out what you want to do with this template. And my suggestion is like once you write stuff, you never start with a template version. You first start with a very specific case, you develop it, you debug it, and then potentially if you feel the need, then you move to the template business, okay? All right. Don't run into the risk of overgeneralization. What happens when you call fill? This fill of M4, like for instance, for the methods, fill M0. What am I calling? Why don't I need to explicitly write the templates? Because this fill, the compiler knows that there is this fill over here. It looks at the list of arguments, M and 0 dot. What is the type of M? The type of M is mat3f. What is the scalar type in math3f? Well, let's go in math3f. Math3f is a math of float 3,4. Let's go to the declaration of math float 3,4. Oh, there is a scalar. Oh, that must be the type. Okay? This is a job of the compiler. Right, so let's go back to here. Then t dot dot scalar. I know what it is. It's a float in this case because that was in my rules. All right, so I have all the data that I need to instantiate the method fill m0. And gets expanded. Now let me introduce you to a new keyword, which is the last one of today, which is inline. Inline is a keyword which is quite powerful because it tells the compiler not to generate the code, to expand the code exactly where you have it. In this way, if you write a complicated matrix expression, there will be no function calls in between. There will be just linear flat code. Then the optimizer, when it sees linear flat code, it does because it has everything in one line and it can basically compress the impossible things in the implementation. So I will write inline everywhere. Of course, you pay, with inline, you pay the fact that, so you write inline only for small, very efficient functions. You don't write inline for huge things. These are all functions that stay in 3, 4 lines. It works also without the inline, eh? Okay, and this is the scala. Compiled. Now, this was the tough version of the exercise because the exercise, the meat of today. Shift F5. Now, templates suck in terms of syntax. They're really ugly. Also, in the case of templates, right now we have seen that the templates divide so we wrote every method inside the class body, right? But also in the case of the templates, you can also detach the two. So have the class body with only the definition of the method, and then have in a separate part of the file, you might have the implementation, right? Only that the rules to tell which template is which are a little bit more heavy. But the mechanism is substantially the same as in the other case. The thing you rarely will need to do that because the problem of the templates is that every time you instantiate a template, you need to include a header file because the template generates code, generates C code, right? And then there is a special mechanism of the linker that realizes when the template is multiply instantiated, checks if it is the same, and then you don't incur in the problem of have multiple instances of the same class, multiple definitions of the same type. This is a special magic of the linker when dealing with the templates. Now, this is over, the lesson part, and now I will feed you with exercises. It's very simple. And we're going to do it maybe now. So I'm asking you to construct a matrix expression where you have a matrix X and you assign the result of an evaluation of C times A plus B. You can write the very same expression where the numbers have the elements have the dimensions that I'm writing on the bottom, or you might also make them different. Then you execute the calculation 1 million or 10 million times, depending on how fast is the machine. And I'm asking you to do the very same thing both in the dynamic and in the static case. Okay? No? So the dynamic case, I think, where do you start from? Well, you start from the exercise directory. Uh, 03 CPP templates, 02 math and vect. You have also the solution, but you don't look at the solution. Inside this folder, I copied the mathf class, and so static math test. Okay, this is the the static version, but you would start from the dynamic, I guess, because it's the dynamic math test.cpp. This is the stub. Set the default font. Okay, remember that the mathf class, of course I provided it to you, mathf.h, is here, and it has all the methods that are defined in the other one. So like basically all what you need to do is to, you also have vecf, h, with all the nice methods that are defined on both cases. And I want you to implement the expression that you find in the slides, which is this. I'll try to copy it, but I will fail. All right? Just that. Of course, the CMake and everything is targeted so that it will compile this thing into a file which is called dynamic math test. Let me see. Control F, lists, static math test, not solution, static math test and basta. Dynamic math test. Zero, zero. Wild. All right. Now it's compiling the solution. You don't want to compile the solution, so you have to edit the make file. I think it's compiling the solution, but you can have a look. You need to compile the solution. No, I don't want to compile the solution. I want just to compile the plain file. Right? So let's see what happens. No, I have only one concurrent, no, 30. Oh, the fill method, I think you have it for free. Maybe. Or if not, vecf. Well, you can also rewrite your fill method. Where was that? What did I do in the solution? Run fill. We have the method run fill attached to the matrix. Now I get it. So mathf has a method which is called run fill. Somewhere. Yes. I wasn't seeing. So you can use that. I mean, of course, don't fill the matrices with 0 because maybe the compiler is marking up and says, no, it's 0. Okay? Just fill them with random values. And remember to profile it at least 1 to 10 million times. So, we need to declare the variable. screen. This is the dynamic case, right? Three, two. Go on. You know what to do, right? And depending on the power of your machine, on whether you're using virtual machine or not, you might need to change the delay loop, the number of times, because I mean I had to pump it to 100 millions on my machine. So. Okay, but if you use a lousy virtual machine, then yeah. I don't know, how much was it? Yeah, this was the number I needed to appreciate something. And this is the dynamic one, right? On my machine, this takes about 16 seconds, the dynamic. And, well, remember to change the CMake. I'm not sure because I'm working on my revision, but you have to edit the CMake in this folder. Oh. You have to edit the CMake in this folder so that when generating the dynamic math test, it doesn't take the solution. So here, you should have written the code, the file that you're editing, not the file that I've given you, right? Is that clear? Otherwise, it's cheating. So why? I change things and this program anyway compiles. So let's see if I have questions on that. Tell me when someone is done. I'm waiting for the first one to finish. Questions? No questions? Or I'm waiting for the first one that tells me the time. To measure the time of a program, from the shell you can write simply time and then the name of the binary. This will start the program, and when it terminates, it tells you how long it expired. My suggestion is that given that the vector, this is the outer product of a vector, v times v transpose, is that you, instead of using a vector, you use a matrix of 3 rows and 1 column. Okay? Because you do v times v transpose, right? And so, like, the vector doesn't have the transpose because the vector is flat. I enabled in the CMake, if you look at the top level CMake, I enabled the build type release. This means pump the optimization up. With this line, you pump the optimization up, but you disable the debugging thing. If you want to debug, you type here debug. You could write the expression as it is, right, guys? You could write this expression here exactly this way, because we implemented the operators. So give me some time. How long does it take? I mean, I can compile the solution and tell you how long it takes to run 100 million iterations on this machine. Time. And now I have OBS running, so it's going to be a little bit longer. Okay, 17 seconds and 53. 400 million iterations on this machine with OBS, with the dynamic one. Okay? I want to have your numbers. Come on.
8.5.
8.5.
10 million iterations.
10 million? No. 10 million iterations. Okay. 8.5, which means 80, which should mean 80 to me, right? So, well, but 10 million, 8 seconds is enough to appreciate the time. With the implementation or with the solution? Did you do it?
Dynamic matrix.
But with yours, you did it.
With your implementation.
Ah, with my implementation.
Yes, because the computer is quite old.
No. I didn't get it. Like, did you do the exercise or you just run the solution?
I did the exercise.
You did the exercise, excellent. So we have one that did the exercise. Come on, I want to have your timings. Also at home? Also at home, give me the timings. Yeah. Well, I mean, I did 100 million, but depending. Yeah. There are people that running to a Raspberry and don't want that. I mean, in order to amortize the loading time of the binary and so on, to appreciate the time, you need to have a time which is at least in the order of 5 to 10 seconds in order to profile it, because otherwise you just measure the time that is required to load the program and so on. Okay, I can give you straight away the time for the implement. Do you agree with me that the implementation by using the templates will be more or less the same in terms of code? It's just like instantiate the matrix of the right size and so on. The expression is supported, everything is the same. I just give you a spoiler. This is still 100 million iteration. I've given you the spoiler. Ah, no, probably no. Was a Okay, that's the time of the static implementation. 17 seconds versus this time. I don't know if you feel it. This is the static implementation. Okay, I mean it's varying because it's the load time that sometimes. Do you? I don't know if you realize what it means. Sedici, 20. Okay, so like we are around 400 million iterations, right? Okay, we are around, but more or less same class of machine, 70, then 22 with OBS. It changes on whether you have a browser that it's running JavaScript on it or not. You know, like on. Remember the light bulbs, right? Now, okay, several people did it. I will show you the solution now, or you can watch the solution yourself. Okay, that's more or less the solution. We declare a matrix 3 by 3, we fill it, we print it, just, no, for cosmesis. We declare a matrix, we call it B, C, no, all of the right sizes, and then we declare a matrix that I call result, but could also be X, and for 100 million times, in my case, we run this calculation. It's interesting because all this thing has been written by us. Now, we're not using a different language or anything. We just defined a new type and new operators on it. Okay? Fine? So this is the static, the dynamic version. The one that does heap allocation, copy constructions, and so on and so forth. Now, I'd like you to start addressing, converting this code to use the other version, which is the static version. Okay. Then just copy it over to know the expression that I have to write. I'm on the static now. Hmm? You have already the example if you want to look at the thing. The example is the robot programming source directory. There is some stuff on how to use this matrix. The example that we have seen already. Like, but it should be clear. Now, this was the example on how to use this. Here we have the usings, but you can also instantiate it directly without the using, if it's more clear to you. Continue. What I would do is to copy the code of the dynamic example and then do some query replace in the end. Are you sure that you're running I know this problem? What are you compiling? Dynamic consent. Is it mine or is it yours? Are you sure like that is the right one compiled in the CMA? No. This code can't compile. This is not a function you presumably, I don't know where you have located this part. But you know anything, can I open this image? Before. If you're confined to the solution, you change, right? Right, and is this the file you have to do? Make it green? Here, like make it green. Make. That's fine. Don't bring them, but take this code and you'll find if it's pointing to the right thing. I got a certain caution of these what I'm sure is that the builders are not reading this voice. Can I? When is it? Yes. And you have a big folder in there. Yes, I created a folder. Yes. But can you build on the top level? The top level thing? I think. Yes, yes, build here. Build here. I'm sure that there is something distributed messages of the open dynamic matters. The less like less dynamic matters. This file is not this file. You reach the folder by some link or whatever, but you're not compiling the rest. You need to use an editor, which is an editor, not an editor script your code, and open straight the file. You're not really on it. That's the problem. Right?
No, credo che sia fatto tanto piccole. Sai che non so perché mi sa che così
Ci sta andando che non stampa su, non ci ha messo le stampe, quindi Okay. All right. Many of you have done something which it's really good. I mean, fine there, or see, or try. Because you do this like remove to be our animal destroy the filter. Our you need always to comply from the top level. I just make you 1 second with the reference with all of everything. Like you should do it from there. Virgola, 3,2. Like if you will have you will enjoy some template errors, which are basically unreadable. My suggestion is to look at the first. Works? All right. Now there's a trick that I have to tell you about this thing. Like, I mean, for those of you that, I think that you have seen the difference when running the template code and the non-template one. But this difference is due to the special case that doing, like, because we had start dynamic allocations, we had all sorts of useless things when we were doing the dynamic matrix. Imagine that to evaluate the expression, we were constantly newing and deleting from the heap, create an object, destroy an object, copy this, copy that. With the templates, we just like managed to write a linear code. Now, in my implementation, in my test, I also did something in the non-template case to see the assembly generated. Was it? Oh. I didn't, but I will. Oh. Ah, was not that this was the dynamic. Now I'm instrumenting the code to add some assembly things so that when I will compile with the assembler, I will look for the commands and I will know what is the fragment generated between the beginning and the end. Okay? This is an extra lesson now that you're doing the exercises. For those in the class that are boom. Okay, this is the assembly generated in the nested loop by the template solution. You might notice that there's an extensive use of the vector extension. XMMS are the vector extensions. You might notice that there is not a single jump. It's a linear piece of code. And you ask yourself, how can this code do the loop, right? In fact, the compiler doesn't do any loop. It realizes that the constants are not changed, the input is not changed, so it's not looping. It's just skipping the entire, it's evaluating the expression once, and it says, given that the input doesn't change, I'm not going to do this loop. Okay? In order to make the compiler, to untrigger the compiler, to make the compiler doing the loop, there is one way, very simple, which is a little bit hitting. Now, I do a plus equals, because a plus equals says, okay, there is something to be done. So now we might expect that there is a slight increase in computation, because the loop is effectively done. Before, the loop was completely ignored. This thanks to the optimizations. And now we will find the loop. Oh, here. This is our evaluation of expression. Presumably, this is the beginning of the loop. No. XMMS, where is it? Routine start, here. This is the beginning of the loop until the end. And we might expect that the compiler will take a little bit longer. So if I now issue a build and launch the static, the loop will be effectively done. And so we're going to see how much it really takes. It takes a little bit, 0.23 seconds. So it's not that the templates are for free. What happened before is that the compiler had enough information, thanks to the static code, to figure out that it didn't have to do that loop anymore, because that variable would have been unchanged during the iterations. So it eliminated completely the loop. Now I forced him to do the loop because instead of writing equals, I wrote plus equals. Notice that this introduces one additional operation in the evaluation as opposite as before. But still, we are at 0.23 seconds, and the other side was 23 seconds. So still 100 times faster for executing the same thing. Or even a more complicated version. So now imagine now that I would say 90% of the programmers do the first version. Imagine that this, with the templates, with this mechanism, you also gain the fact that you can run this code on the GPU, should you need. Because it's linear code, there is no branching. The GPU core, they don't like branching. They like, straight things. So you have loop unrolling. In fact, you could copy it and write a CUDA kernel that executes this expression for you. Okay? On the one end. So we have seen template for speed, and this was due to the loop unrolling. And we also have seen we will see in the other exercises, and then I say hello to everybody. We will also see templates for generalization. The other exercise that I subminister you, they are all very fast. I hope you appreciated that it's something that you can sit and do in half an hour, or even less. I would like you to write a class myItem with a special comparison operator that is defined in here, and then instantiate the tree with this class, the binary keys. Before we used myS, now we use another thing. No? Okay? And then this is just a lexicographical comparison. So it compares I1 with I2, like float F double string S. Yeah. It compares the float value. If the float value is the same, it compares the strings. String is a type of CPP, or it's a type defined in the standard library. Includes string, std string. Okay? And supports the comparison and all the rest. And the last one that would be in the fog is that add the remove operation to the template class. Because if we can insert, we can also remove. Right? This concludes the exercises, and I would say concludes the day for you and for me in this sense, so that you have 20 minutes to recover. If you want to play, I'll stay around. And I close the streaming, if there are no questions.